Hello and welcome to Video Notes 4.2, where we're going to talk about a one-sample t-test, okay? So what is a t-test? Well, that's one of our vocab words. It's actually called the student's t-test, or t-model, I should say. There's also this new thing called degrees of freedom, standard error of means, and a t-score to go along with the t-model. Our calculator maneuvers, we've got a couple of them. We're going to figure out how we can find a p-value from the student's t-model, and how do we run this one sample t-test that our notes are named after. Recall that we can use the normal model to approximate sampling distributions of means or proportions, as our last video noticed, and that's totally fine as long as we check off those conditions of randomization, independence, and having something that is, either approximately normal population or a big enough sample size. But we also actually need to know what is the true population's standard deviation. So notice that that formula there has sigma sub x standing for sigma, the population's standard deviation. Well, that third condition about it being from a normal population with a known standard deviation could be a bit problematic if we do not know the population's standard deviation, which seems pretty likely, actually, because if we did know the standard deviation for the whole population, then we probably know a lot of stuff about the population, and then our analysis isn't really that important necessarily. There is some stuff that we do know, like we have so much data about the birth weight and birth length of babies all across the world that we basically have the whole population, and it's good enough to sort of use that data to calculate a population standard deviation. But most of the time we're grabbing from unknown populations. So if we're always running into this situation, what is it that we're going to do? Okay, well, we need a new model. This model is called the student's t model. If you're interested in figuring out where it came from, do a quick Google, throw it into ChatGPT, and ask it, where did this student's t model come from? So what I have in front of us are sort of three different examples that are comparing the normal model to the student's t model depending upon sample size. So sample size for this first one here, so we can see that's in red, there is sort of this shorter curve with these longer tails, and then in this bluish green or teal color there, that's the normal model for all three examples. So this first one has a sample size of just 2, and you can see that its degrees of freedom are 1. DF stands for degrees of freedom. We'll get into that a little bit more in a moment. So you can see that just a sample size of 2, which is not a lot. We have really fat tails is what they call it, actually. And it's a little bit shorter there to make up for that fat tail. Still has the same area under it. It's an area of 1 under this curve, just like the normal model. And because of those fatter tails, it's just a little bit shrunkified. And then this middle version here, degrees of freedom is 5, which would mean our actual sample size is 6. Seeing a pattern here about how to find degrees of freedom. And then, so you can see here, tail's not quite as fat, but they're still a little bit fatter than the normal model. Not quite as tall as the normal model there in the center, but it's definitely taller than the one for a sample size of 2. And then as we move along here, this last one is a sample size of 30. So I think you definitely now know how to find degrees of freedom. And at this point, it's almost impossible to tell the difference between these, the normal model and the t model here. They kind of look exactly the same. You can kind of see, if you look closely and squint, that normal model peeking out a bit on top at the peak there, peeked down a little bit down towards those sort of tails at the bottom, but it is not, but it is pretty close to each other here. So what did we sort of learn from this and from sort of our work in the applet in class? Well, we learned that a student t model is essentially just a shorter and wider normal distribution to adjust for that fact that you don't know the true standard deviation. Thus, you have a little more uncertainty uncertainty, I think I spelled that right, in your sample's estimate of the true population standard deviation, because you're using the sample's standard deviation in this case as just a replacement for the population standard deviation. And it's possible that they are very, very close to each other, but it's also possible your sample maybe had an outlier or something that really might mess with things. So because of this sampling variability, just like your sample mean might ping pong around, pulling sample to sample, it's the same as your standard deviation. Every time you pull a new sample, your standard deviation for that sample is going to be a little bit different, okay? So we have to sort of think about pushing a little more data out into the tails to account for this uncertainty that we were talking about. Your model is just going to be a little less precise, and that's rightfully so. So it's not like we're in trouble here. It's okay. We're going to be a little more conservative with our probabilities here, okay? So as we saw above here, the amount that you sort of widen your curve really depends on how large your sample size is going to be. And then we're going to use what we call our degrees of freedom, which is, as we noted above, you probably noticed, subtracts 1 from your sample size. So in other words, df is equal to n minus 1. And we also noticed from sort of labeling the things up above here, hopefully, is that as the sample size increases and thus the degrees of freedom are increasing, that curve gets a little bit narrower. Okay, those tails sort of flatten out. And it gets a little bit taller in that center part there and gets closer and closer to that standard normal distribution. In fact, theoretically, if we had an infinite number of degrees of freedom, then it actually becomes the perfect normal model. That'll become important to us when we get into something called confidence intervals a little bit later this unit. So what's the big sort of, why does this matter sort of thing? So if you don't know the true population standard deviation for the mean, which again is pretty much always the case other than in scenarios where there's been like hundreds of years of data being collected, then you must estimate the sample standard deviation. You must estimate the standard error based off of the sample standard deviation. And because we're calling that and because we're using the sample's standard deviation and not the population, we have a small language change here. Instead of calling it the sample standard, instead of calling it the standard deviation of means for our sampling distribution, we change it to the standard error. Error kind of implying that we think it's off. It's not for sure. We're just saying that it's off. I mean, it kind of means the same thing. A deviation and an error are kind of similar in ideas here. I don't know who decided that there had to be a language change, but it has happened. So, and so the formula for that is, so we're going to call it S sub x bar here. So this is standard error of means. X bar, remember, is a sample mean, is equal to the standard deviation of the sample, S sub x, divided by the square root of n. And if that looks familiar to you, well, that's because it's just a slight reframing of this up here. I'll erase what was already there and circle it again. So you can see that that has the exact same structure when we compare them to each other. So all you're doing is doing a swap out. Instead of your numerator being the population standard deviation, we have to use the sample's standard deviation. And again, if you're like, man, all these formulas, I have to memorize them all. No, you do not. It is on the formula sheet. Let's click over and look really quickly. Where could we find it? Same place we were finding stuff about our z-test last class. So we're going to scroll down because we're not looking at proportions, we're looking at means. And we can see that right here, if we're dealing with one population, which we are, then we're centered at the mean of the population. If we know sigma, the population standard deviation, then we find our standard deviation for our sampling distribution with this one. But that's not where we are today. Today we are over here because we do not know our population standard deviation. So there's your formula. All right, so let's use our new knowledge to help us sort of side-by-side compare the calculations that go into it, depending upon whether we know the population standard deviation or we don't. So for this one, we're going to find the probability of a random group of 16 college students having an average grade above a 75% if, so part A, their class of 197 students, that's the whole population, has an average score of 70% and a known standard deviation of 10%, and graded on a, basic normal curve here. So let's sort of mark out the things we do know. So we know that the sampling distribution will be centered at the same place as the population, which is 70%. And yes, it is a percentage, so we could talk about this in terms of proportions, but it is an average of grades, so it's actually makes more sense to think about it as a mean, right? So pay attention to that word average every once in a while. It'll pop up for you, even if they give something as a percentage, because it is like an average of maybe multiple percentages being combined together. And then we're going to find our standard deviation for the sampling distribution, which, since we know the standard deviation for the population in our formula here, we're going with this one. Let's keep circling in this exact same color, which is not helpful at all. Let me erase, and actually I'll go with this. We're going to use that formula there because it says we have a known standard deviation for the population. So let's go ahead and calculate that. That's going to be the standard deviation of the population divided by the square root of n, so in this case 10, over the square root of 16. That gets us 2.5. Excellent. So now we're ready to move on to finding our test statistic. This is a normal curve, so we are using a z statistic, and that is going to be our observation of 75% for the sample, minus 70 over the standard deviation for the sampling distribution, 2.5, getting us 2.00. So z is 2.00, our z-score. And then now to find our probability p-value here, we need to think about the normal curve. This is where we can jump over to our z-table or use the normal CDF function in our calculator. You do whatever you'd like to do as I sort of draw the idea of what we're doing and come up with the value from all of this. All right, so if you haven't quite caught up or you're still working on it, pause, but I wrote down all the things here, drew the little diagram. We got our normal curve, and then the probability that z is 2 or higher comes out to about 0.028 using the table. Might be a little bit different if you use the normal CDF function, although probably not, because our z-value was exactly 2, so probably should be exactly the same. All right, so that is if we know the standard deviation of the population. As I've been pointing out several times throughout all this, that is usually not the case. Let's look at an example and see how do our calculations change based off of that different information. So here now, we got our population of 197 students, still looking at the average score. We know it is a 70%, so pause, I'm gonna write that down. Mu of x bar is still 70. But the standard deviation of the population of all 197 students is unknown, okay? But we do know that this sample of 16 students randomly polled has a sample standard deviation of 10%. Okay, so now to find my standard error, this time around. Same kind of formula structure, right? But I'm going to end up using that 10% as a standard deviation for a sample. So I'm going S sub x over the square root of n, which is 10 over the square root of 16, which is still 2.5. So we have the exact same mean and standard deviation error for this distribution. We're going to see how our probabilities might change, though. All right, next step, though, let's find our t-score. So t, and then my subset is going to be the degrees of freedom. So we usually write t with a little subset here on our degrees of freedom. In this case, 16 minus 1 is 15. So that's a great way to denote your standard or your degrees of freedom right there. And the calculation for a t statistic is exactly the same for a z statistic. It is not a different formula. How do you know that? Well, if we go back over to our formula sheet and actually go over to page 1, as I pointed out in the video last time, our standardized test statistic is always this formula right here. It never changes from z or to t at all. So that's really important to keep in mind, is that the structure of this is exactly the same. So we're going to go that we found a sample of 75 compared to the mean of 70 over 2.5, which still gets us 2.00 as our t statistic this time. And how are we going to find this? Well, let's visualize it first here. So a normal curve, looks like that. But as we noted, the student's t model looks basically the same. I don't really need to change how I draw the shape of things here. It's still going to be the same. It's still centered at 0 because this is a standardized score here. It's still going to have a standard error in this case of 1. And I'm still interested in, well, what's all this area to the right of 2? So how is this going to change? Well, the only thing that changes is I need to think about using a t distribution, which is not quite the same as a z. It gets closer as I have more students, but I only have 16 students. So if I look back up here, my model is a red curve that kind of falls somewhere in between these two things here. So what does that look like? Well, the good news is that your calculator can find this for you. We don't have a table that can do it for us. There is a table associated with t-scores. It's not helpful for what we're about to do now, so we need to jump over to the calculator. Let's do that. So much like normal curves, we could use our test statistic and our distribution table, z table for first semester, and anytime you're dealing with a normal curve, to find probabilities. But you could also use the calculator as sort of a different way to do it using normal CDF. Well, you can do that with t scores as well. So let's go ahead and see how we would do that with our t's. So we'll go second, and we would go to vars, or distributions is actually where it's going to send us. And you can see, like the normal functions, we also have t PDF and t CDF. We're going to deal with CDF. We're always doing cumulative, since these are continuous random variables that we're dealing with and not discrete. So here we're going to be clicking enter. And if you don't have the menu I'm staring at here, maybe you have some older software, the syntax is this order here, which is lower, upper degrees of freedom separated by commas. So in our particular case, our lower bound actually is the test statistic that we did find, which is a 2.00 to be specific. And then our upper is actually infinity, but we're just going to press a bunch of 9s until we get tired. And then degrees of freedom. Degrees of freedom is n minus 1. So we had 16 students, that is going to be 15. And then we'll hit paste. So here, if you were, again, typing it in and you didn't see that menu, this is the syntax you'd be staring at here. TCDF, lower bound, comma, upper bound, comma, degrees of freedom. And now we hit enter. And we get 0.03197. So that gets us a p-value of 0.0320. So that is how you use a t-distribution to find a p-value, okay? So you might notice, hey, that's not the exact same value that we got over in part A. Yeah, it's a little bit higher of a probability, and that should make sense because if we have more uncertainty, we probably will be a little more conservative with our probabilities. So we'll be thinking like, maybe it's a little more likely actually than if we did know the whole population's standard deviation. So a little bit higher probability just to kind of cover our butts is kind of what's happening there. Let's flip over to the backside. So let's go ahead and try a problem out where I'll leave a good amount of it kind of blank for you to kind of figure out. So here's the context. A tire manufacturer is considering a redesigned tread pattern for its all-weather tires. Tests have indicated that these tires will provide better gas mileage and longer tread life. The last remaining test is braking effectiveness. The company's current tire model allows a car traveling at 60 miles per hour to come to a complete stop with an average of 125 feet after brakes are applied. The company will only adopt this new tread pattern if there's strong evidence that it improves upon that benchmark. Based on the data from 10 random stops given below, should the company adopt the new tread pattern? Let's provide statistical evidence at an alpha level of 0.05. So they give us data. So what you want to do is to first plug that into your list and run a one variable stats test because we're going to need that information in a little bit. Pause the video so that way you can do that. Now that you have done that, hopefully, let's go ahead and continue along here. So let's state. Remember that's stating our hypotheses, defining our variable. So let's talk, what is our null hypothesis? Well, the null hypothesis is sort of that status quo, the no difference. So the old pattern has a stop distance of an average of 125 feet. And we're only willing to accept this new tread pattern if, in fact, that average falls below that benchmark. And to define it, this is where mu is the mean stopping distance for the new tires. Excellent. Let's move on to plan. Plan, that's where we're going to say what procedure we're about to go through with and check all appropriate conditions. The name of the notes is exactly the procedure we are going to do. We're doing a one sample t-test. Conditions. They're exactly the same as the one proportion z-test. You need to check off randomization. You need to check off the idea of independence, and you need to check off approximately normal. You can do that by rereading the situation, thinking about different ways of checking those things. I will tell you, the normality one, a little bit tricky, something we haven't done a ton of. So I'll give you a hint. Why don't you go back to your notes where we checked normality, the nearly normal condition, way back in, I think it was Unit 1. So take a look in your notes to see if you can find that. If not, we'll talk about it in class. All right, so hopefully you've got conditions checked. You've tried your best on those. Let's move down to the do step here. So do, I will do it by hand as I did with the z-test in the last notes, but I will show you the calculator maneuvers here in a moment. So do, we have a mean for our sampling distribution at 125. That is where the population, the null population, is sort of centered at here. And then we don't know the standard deviation of the population. It is not given to us, but that's why I had you plug your data into your calculator, because you could come up with the sample standard deviation to come up with our S sub x bar. So in your calculator, it should have told you S sub x. Remember, you don't want sigma sub x, you want S because we're treating it as a sample. And that, in the calculator, says is 2.7809 all over the square root of, and we have 10 tires that have been sampled here. If I go over to my calculator and plug that in, I get 0.8794. All right, so let's go ahead and find our t statistic, just like we would our z statistic. So t sub, what's our degrees of freedom? 9. 10 minus 1 is 9. And so that's going to be our x bar minus the mu sub x bar over s sub x bar. Or in other words, we've got a, well, back over to my calculator, it said that my sample my sample mean x bar was 124.2. And then I'm going to subtract that from mu and divide it all by this standard error of 0.8794. And out pops my answer of, it's negative 0.9097. That's our t statistic for all of this. So now that we have the t statistic, and based off of what we did on the front side here, we should be able to come up with this p-value. Take a moment, go over to your calculator, run a t-CDF, see what you come up with your p-value, then head back over to see what I came up with. All right, and so I drew out here the t curve. Looks like a normal curve, basically. Shaded in this region. We're looking to the left of negative 9.9097 because we're interested in the stopping distances less than. And using my calculator and the t-CDF function, I got 0.1933. So about a 19% chance for this, which is going to be helpful in my conclusion in a moment here. But you might be wondering, can the calculator run the test and find all these numbers for me? Or do I always have to do it by hand? Well, it can do it for you. Let's take a look at how that happens. So like we could run a one proportion z test on a calculator, we can also do a one sample t test on a calculator. Let's hit Stat and go over to the Tests menu, like we found one prop z test. This time around, we're looking for a one sample t-test. You might notice, wait a minute, there's only two sample t-tests. What's the one sample? Actually, that is number 2. That is the same thing as a one sample t-test. So we hit Enter, and so there's a couple of ways you could do this. You could use data. That's going to use your lists, if you click on that. So for this one, you could have entered all the data into your lists, okay? And that's what you would have had to have done in order to be able to find the sample standard deviation. So if you wanted to continue on with it using data, totally fine. But I actually don't have the data in my list anymore, so I'm going to go over here to Stats. But I think you can see here, like, you just got to tell it where to look. But I'm going to go over to Stats. Since I have all that, I worked it all out in my green video notes there. So let's go ahead and type in these things. What is the null mu? Well, the null mu that was given to us was 125. And our sample spat out at us 124.5. Sorry, 124.2. That was the sample mean. Sx, that's our sample standard deviation. So notice I am not writing in the sampling distribution's standard deviation. So here I do not want to put in what I calculated of 0.8794. I'm putting in the 2.7809 number because it will automatically do the calculation for me. So 2.7809 is what I got for the sample standard deviation, okay? It is a small difference, but like right there, you can see that like it says S sub X, not S sub X bar. So it's that small difference there, like this is the sample of my values here, or the standard deviation of my values. S sub x bar would be the standard deviation or standard error of the sampling distribution. Sample size here in this case was 10. Again, you don't have to type in degrees of freedom here. You can type in the sample size, and they will automatically calculate those degrees of freedom for you. And then the last thing is, what is our alternative hypothesis? Are we saying different than, less than, or greater than that 125? And our wonder is about it being less than. And down here, as we did with the z-test, we can do either calculate or draw. So if you're looking for a visual, maybe the problem asks about drawing a visual, you can go there. But this problem is just about calculating, so I'll hit enter. And there you have it. Our t is negative 0.9097. That is what we found with our by hand work. And p is 0.1933, which is what we also found from our CDF function. And then it restates the sample mean, the sample standard deviation, and our sample size afterwards. So what is necessary here? Well, when you're going to write down the pieces for this, so if you're going to go calculator mode only for this in the do step, and you're just going to write down what it spits out to you, you must have the following. You must have your test statistic, t. So just like we had to have z before, it's t this time. You need your p-value, okay? And then something that doesn't show up on here at all, but needs to be written down to get full credit for the do step, is the degrees of freedom. So I would need to write down somewhere df equals 9, or as I did in my work there, t sub 9. It is understood that that little subset on my work is the degrees of freedom, and so that counts as displaying the degrees of freedom. So if you're going to copy from here, I would write down t and p and df, and then be done with the work if I needed to. So at this point, because you have your p-value and there was an alpha value or an alpha level already established earlier, you can make your conclusion. It's not any different for a t-test as it is for a z-test. So your goal to show in class is that you have tried to check off all the conditions appropriately and made an appropriate conclusion for this. And we will talk about more of these things in class.